Well, hello everybody. Welcome to Friday. Yay, it's Friday. Today we're going to talk about star trails. What can we learn from star trails? Once again, another nail in the coffin for flat Earth. Trying to figure out how many nails we need. Oops. Too far. So from the northern star trails, you guys have seen this picture probably 100 times. We all know that in the northern hemisphere, facing north, you see star trails moving counterclockwise. In this picture, they're going from around this way. Star trails apparently circle Polaris. That's what we see. That's the view we get. Polaris is in the middle. It moves very little. If you're looking for Polaris, the two outer stars in the bowl of the Big Dipper always point to Polaris. Polaris is at the end of the handle of the Little Dipper, so that'll give you some references so you can look for Polaris in the sky. This angle right here between Polaris and the horizon is always equal to your latitude. So at the North Pole, Polaris will be almost directly overhead. At the equator, Polaris will be very near the horizon, and then it moves every place in between. So it's always at your latitude. So if we look at these stars moving counterclockwise, right, you can see these circles. On a flat Earth with stars affixed to a rotating dome, so the dome is rotating this way, you're not ever going to see these circles, and for sure you're not going to see the stars moving from right to left up here. So they're moving this way, right to left, and then close to the horizon, they're moving from left to right. So tell me how that works on a solid dome that's rotating. Okay, guys? One thing that we often see is the southern star trails in the southern hemisphere. Facing south, you're going to see star trails circling clockwise like this. Polaris is not visible anywhere in the southern hemisphere. Sigma Octantis is close to the center of the circle of these star trails. However, it's just barely visible to the naked eye. If you're trying to look for it, guys, you can use the major stars in the constellation Octans. And again, the angle between Sigma Octantis and the horizon is your latitude in the southern hemisphere. So just like Polaris gives you latitude in the northern hemisphere, Sigma Octantis gives you latitude in the southern hemisphere. Again, like I said previously, on a flat Earth with stars affixed to a rotating dome, you could never see stars circling backwards here at the horizon. So you have stars rotating from left to right up here, and then down at near the horizon, these star trails will circle around from right to left. So once again, tell me how that works on a flat dome. And then we have equatorial star trails, which nobody ever mentions. Nobody talks about these because they just don't fit anywhere. This picture I got from this location, and you notice that it has a great circle about the star trails. You can read this paragraph. So on the right you have star trails that are rotating clockwise. On the left they're rotating counterclockwise. In the middle they're going straight up. Once again, I just don't see how this can happen on a rotating solid dome. Let's talk about the planets a little bit because they look like stars in the sky. I got this text from this website. So in their apparent motions across the sky, the planets behave somewhat like the sun, but their motions are more complex. So they don't just move from east to west. The planets follow a westward diurnal path along with the stars. Daily, the planets rise in the east and set in the west, just like we're used to. All planets follow nearly the same path along the ecliptic at 23.5 degrees. And if you don't recognize that number, that happens to be the same as the tilt of the Earth. So what you would see in the sky if you could see all the planets at once is that they're all on a line at an angle in the sky. All of the planets move gradually eastward among the stars. By this I mean night to night, not on the same night. So if you look at them at the same time from the same place on different nights, they will move gradually eastward. However, interestingly, some of them show a retrograde motion for short periods of time. So this is retrograde motion, means they're moving back from west to east. So somehow they move along east to west, and then they go back west to east, and then they go back east to west. This is explained by the different orbits of the different planets. Some are closer to the sun, some are further away, and so the Earth overtakes and passes them in our journey around the sun. The planets follow Kepler's laws in their motions around the sun. You can look up Kepler's laws. It's a little complicated for this video. The spacing of the planets follows Bode's law, which again you can look up. So therefore, as viewed from the Earth, the planets move at different speeds. Again, I mean over time, not on one single night. And once again, the planets just can't be affixed to a rotating dome. There's just no way that it can be explained by a rotating dome. The sun and the moon, not really planets or stars, but the sun and the moon also move along those same star trails. In this picture here, we have the star trails, and this is the moon rising. So you can see that the moon follows those same star trails. Of course, you can't see the sun's trail during the night. So both of them, the sun and the moon, follow these same star trails. In my first video, if you watched that a while back, I showed that the latitude is also equal to 90 degrees minus the sun's angle from vertical at solar noon on either solstice. So that's a little complicated, but if you stand and at high noon or solar noon, if you measure the angle from the vertical, so from straight overhead, and then subtract that from 90, you get your latitude. Once again, you know, all these numbers are all lining up the same. It follows a very clear rotation day in and day out. So if you observe the moon, again from night to night, it rises later each day, which means that the moon is moving at a different rotation in relation to the Earth. So here are some arguments I'm always hearing from flat earthers. They always say perspective. Everything is caused by perspective. So again, you can see these star trails that rise and set and arc across the sky in very short paths, not the path across the sky horizon to horizon that the sun and moon make. There's often complete circles like we saw in the earlier pictures, which requires a backward and forward motion. And again, how can you explain that with a rotating dome? The second one I always hear is the light fixture in the room argument, where they have ceiling light, and if you stand on one side, you see a different part of the light fixture than if you stand on the other side. First of all, you're looking toward the center of the room, you know, center, instead of, if like we're standing on the Earth, we're standing back to back. In the northern hemisphere, you're looking north. In the southern hemisphere, you're looking south. So if you were in this room, you'd be looking at the wall. Secondly, in the room, it's a fixed light, and you're not seeing the star trails and how they move. All you're seeing is a fixed position. And then, of course, we have the old, when you're looking at the sky from different locations, you should see the same stars if we're on a sphere. That's not true. As the Earth rotates, you're definitely going to see the stars changing through the night, rising and setting in varying arcs. On a flat, non-rotating Earth with the old rotating dome, it would necessarily require star trails level with the horizon. So no matter where they are in the sky, they should be moving from right to left or east to west everywhere. So in conclusion for this video, star trails 100% prove a spherical rotating Earth. There are just too many lights in the heavens to be explained by a flat, motionless Earth surrounded by a rotating dome. And my favorite thing to think about when I look at the sky is that the sun, the moon, the planets, and the stars all move across the sky in concert in a beautiful choreographed dance, rising, setting, moving in retrograde motions, way too complex for a simplistic process such as flat Earth. One final credit, you need to check out Wade's Underworld video. He's talking about the same kind of things with the star trails and the tilt of the Earth, and he does a much better job of showing in pictures, and I encourage you to look at that video. I'll have the link in the description. Like I said here on the screen, I dare you to watch it. That's all for today, and I hope you learned something. Give me a shout out.